welcome to our session for physical sciences. My name is Themba Ncube. Today we're looking at something very exciting that has to do with exploring, magnetic forces between materials. So it's all about the magnets, the science behind it. It will also, tap into some of the, the concepts or the ideas that we would have maybe discussed in our earlier grades, and try to think deeply and more about them in terms of exactly why do we make certain observations. So we'll continue also to make some predictions based on the behavior of magnets when magnets interact with each other. Now, without much further ado, let's look into the the mind map. The big idea is in terms of where we're going with the concepts of magnetism, right? Okay, right. So the thinking exercise, maybe something that's going to definitely guide our discussion today. This is the thought for the day. Have you ever thought about what causes magnets to repel? So it talks about repulsion and attraction between two magnets that interact with each other. And number two, what causes magnets to attract certain materials? So this is talking about the materials, which has a lot to do with the physical properties. So it says what causes magnets to attract certain materials but have no effect on others. So the no effect, again, it's in terms of classification. We are looking at magnetic and non-magnetic materials. So this is the big idea. Now let's look at the concept map, okay? So the main thing that we're focusing on, because there are a lot of aspects in as far as magnetism is concerned, we'll focus our attention on the non-contact forces. This is because we are exploring forces of magnetic materials and magnets. So it has to do with the attraction, which is a force, as well as repulsion. So this is the main focus for today's session. So it has to do with non-contact forces. And it's when we talk about non-contact, exactly what are we talking about? We're talking about two materials or objects, exerting a force on each other. And think about a force as, a push or a pull. This will obviously, as we zoom in, would understand how two magnets interact with each other in space. All right. Okay. Now, the non-contact forces that we may have heard, or maybe briefly alluded to earlier in some of the, the earlier grades or in previous sessions that we've had, we may have heard about electrostatic forces, which has to do with charges, right? This one has to do with charges. Okay, charges, we're talking positive and negative charged objects or particles. We talk about spheres. So if we talk electrostatics, it has to do with charges. Static suggests that this charge is stationary, okay? So these are stationary charges. Stationary meaning not moving, okay? So this talks about charges. What about the gravitational non-contact force? Have you ever asked yourself why objects tend to fall towards the center of the earth? It's because the center of the earth, or the core of the earth, tends to pull objects towards its center. So that pull is actually a gravitational force, and that force actually acts towards the center of the earth. Hence we say the objects are in a gravitational field. So gravity as a phenomenon has to do also, or is the consequence of what we see when objects tend to fall towards the center of the earth. Right. So this has to do with, the attraction. This is about just attraction, okay, between objects, okay? So this is a force, again, of attraction, okay, between objects. This has to do with objects. It has nothing to do with charges. So this is about objects. So, but our focus for today is magnetism. Magnetism also, maybe just to allude to it, we also want to think about in terms of forces. So today we're talking about forces of magnetic material, and these forces are non-contact, either attraction, okay, attraction, which is the pulling together, or repulsion. Okay. So there's a very urgent need for us to actually appreciate the different types of non-contact forces. Magnets exert non-contact forces on each other. Charges exert non-contact forces on each other. Objects also exert a non-contact force of attraction only, which separates it from magnetic and electrostatic forces. Right. Okay. Now, let's talk about observation about magnetic forces, because our main idea today is to explore the forces around magnets. Okay. So when we look at observation entails, a number of actions during a scientific process or during an investigation. It could be an experiment. When you observe, you note the effect, of changing one quantity as to how it affects the other. Secondly, you also note about, the effect of having two magnets interacting with each other. So observation has to do with what we see, what we hear, what we smell, what we feel. So observation is quite broad, and these observations can lead us to actually make some, some informed or some guided predictions in a way. So if we talk about observation about magnetic forces, think about it. So you know that magnets have got two poles, the North Pole and the South Pole. Now the term that describes the existence of the two poles is the term dipole. Okay, so every magnet is actually a dipole. What do we mean when we say a magnet is a dipole? It means every magnetic material or every object that behaves like a magnet or that has got magnetic properties actually consists of two poles, which is the north and the south. And the two poles can never be separated without that material not losing its magnetic properties, right? So the word di suggests that there is two poles, all right? It suggests that there is two poles. So magnets, its effect have north and the south pole. So the material does not appear any different at the pole. If you look at a magnet, let's say we have a bar magnet, okay, except for the color code, which is, in this case, we've got the south blue, north red, this is just for the color coding. But when you look at the two poles, they actually look the same. Nothing distinguishes in terms of structurally or otherwise. It means they look the same. So the magnet is essentially a dipole. What do we mean by that? We are saying that every magnet contains two opposite poles, which is the north as well as the south. Right. So the material does not appear different at the poles. That's an observation about a magnet. Okay. Now, what happens, okay, when the north pole of magnets are brought close to each other? Right. Now, this is an action that is carried out. You've got two magnets. Each one of them is a dipole. Right. Now, we've got two poles. They are brought closer to each other, but without necessarily making contact with each other. So the prediction is such that if you have got two magnets, you take two poles. In this case, we've got two like poles. These are like, okay, or similar poles. Okay, these are like or similar poles, right? Why do we say these are like poles? Because it's north and north, okay? So the north and north, what happens? These two, they tend to push each other away. So the force that is relevant in this case, in terms of the observation, is that as these two push each other away, we're saying that they actually repel. So these two will actually push each other, okay, away, okay? So what does that mean? It means the north pole of magnet A pushes away the north pole of magnet B. So these two poles, they tend to repel each other. So there's a force of repulsion. So there's a force of repulsion. Okay? So this is the observation that even if you try to bring them closer, what happens? They tend to push even harder away. All right. And then what happens when the south poles, now we've got two south poles of two magnets. We still have magnet 1 and magnet 2, right? So these two are brought closer to each other. Remember, as we bring them closer to each other, we emphasize on the fact that there is no contact between them, right? So these two do not have to come into contact, right? Now, these again are like, okay, these again are like poles. The other word for like pole is similar poles. They're similar or same poles. So these two, they tend to push each other away. So again, they're still pushing away, right? That's the observation. So if we had two magnets and we try to demonstrate this, this is the very same observation that we'll make. Again, these are like poles, right? And then moving ahead, what happens when the south pole of one magnet is brought close, okay? Again, no contact. Now we've got the north pole and the other pole, which is the south, right? Now, one thing that's going to be different here is that these are opposite. These are actually opposite poles. Opposite or unlike poles. Okay. So these are unlike poles. Now, what happens? The other one pulls the other. Let's say this is magnet 1 and that is magnet 2. Now, let's describe what exactly is going to be observed there. What is going to happen is that magnet 1 pulls magnet 2 towards itself. So this is the force exerted by magnet 1 on magnet 2. Now, on the other hand, let's think about the force exerted by magnet 2 on magnet 1. Okay, magnet 1 is attracting magnet 2 towards it. In other words, it's pulling magnet 1 towards it, right? So the force of attraction by magnet 1 on magnet 2 is equal to that of magnet 2 on magnet 1. So the idea is that these two, they exert a force on each other, irrespective of size. Whether magnet 1 is smaller than magnet 2, whatever force that 1 exerts on 2, 2 will exert on 1, and vice versa, right? So here, what are we saying? We are saying these two will pull towards each other, okay? Pull towards each other. I think on the basis of the fact that we know that a force is a pull or a push. In this case, they are pulling towards, while in the two earlier scenarios, it's actually pushing away, right? So we're still consistent in terms of the language to say that a force is essentially a push or a pull, right? Now, in the nutshell, we've realized that when we talk about like poles, it can be either north and north or south and south. That's like, in both cases, there are similar poles. But remember, there are two possibilities. It can be both north poles or both south poles. In both cases, those are similar or like poles. What about opposite? Opposite is north-south or south-north. The order is not very important. The fact remains that these two are actually opposite poles. Okay? Now, this is the summary of the observations that we talk about. Okay? Now, magnet 1, if we had the north and north, okay? So this is north and north, okay? The force is repulsion. What about if we had south and south? The force is repulsion. And in both cases, repulsion, we're saying, is pushing away. This is what we'd observe, okay? So this is pushing away, okay? This is pushing away. These two are actually pushing away because these are like poles. What about south and north? Similarly, which is north and south, because we're saying we're not paying attention to the order. This is pulling towards each other, okay? This is the actual description of the observation, pulling towards, okay, each other, right? Now, in a nutshell, what are we saying? What are we saying? We are saying that in conclusion, after all's been said and done, we are saying like poles, they repel each other. This is north and north, south and south, or south and south. While at the same time, we're saying opposite or unlike poles, they tend to attract each other. So this is the long and short of it, okay? So if we talk about the factors that affect the size of the magnetic force, right? What is important is for us to understand that when we talk about factors, we are actually talking about quantities, or what dimensions, or what is it that about the magnet that affects the magnitude or the size of the force. So because of time constraints, we'll take a short breather for now, and then we'll take our discussion from what exactly, in terms of what exactly affects the magnitude of the magnetic force between two magnets. Having said that, let's take a short break for now. Welcome back to our second segment. We're still discussing, exploring as well the forces that exist between magnets. One of the things that we also tapped into in our first segment, we spoke about the interaction between poles, having said that every magnet is actually a dipole, meaning that it has got two opposite poles, the north and south. And then the observation that you would make when you take two like poles, it could be the north and north or south and south, they tend to push each other away, and we arrived at a conclusion that any like poles that are brought closer to each other, they tend to repel each other, while when we spoke about the opposite, which is unlike poles, your north and south, south and north, it doesn't matter the order, we are saying that those two would actually pull towards each other, because that's attraction. Attraction is pulling together. Right. Now, before we went for the short break, we also spoke about briefly that we want to understand how this magnetic force changes and what exactly, affects the magnitude or the size of the magnetic force. So based on those observations, let's say for argument's sake, we've got two opposite poles, the south and the north. That's magnet 1 and magnet 2, right? Just to label them. And then what factors affect the size of the force? The force in this case is a force of attraction, okay? It's a force of attraction, right? So these two are actually pulling towards each other, okay? So these are actually pulling towards each other, okay? So what affects the size of the force? Okay, now the force that magnet 1 attracts magnet 2 is actually equal to the force that magnet 2 attracts magnet 1. So if in terms of the size sometimes we would refer to size as the magnitude, right? Okay, we want to know what affects the size, or how big it will be the force if these two were brought even closer or further away. What if we used different magnets which are stronger or weaker? So that's the main point for discussion. So the type of magnet affects the size of the force, okay? So the type of the magnet here, we talk about the strength of the magnet, okay? There are strong and weak magnets, okay? So a stronger magnet would actually attract with a greater force, attract another magnet with a greater force because of its strength. And then the distance between the magnet. Now, the closer they are, this greater the force. The closer, because remember we said these two must not come into contact. We're just bringing them closer and closer without necessarily them coming into contact. So the distance between the magnets also affect the size of the force. So the closer they are, the closer the two magnets are, okay? The two magnets, okay? The greater the force, okay? The greater, okay? The greater the force. So what exactly do we mean? If the same magnets were at a distance 10 centimeters, they would exert a force of attraction on each other of certain magnitude. But if we halve the distance, let's say to 5 centimeters, we expect the force to be correspondingly greater. So at a greater distance, lesser force. At a smaller distance, greater force. So distance between the magnet and type are actually the two factors that will determine the strength of, the size of the force of attraction or repulsion, right? Okay. Now, we're still talking non-contact forces, okay? Because because our emphasis was that these magnets are not coming into contact. And we're still within the discussion on the type of forces, which is attraction and repulsion. So this is for opposite poles, okay? Opposite or unlike poles, okay? That's the main idea, okay? While, okay, this is opposite poles, and then this one has to do with like, okay? Like poles, okay? So this is the big idea in as far as the non-contact magnetic forces. Now, observation about magnetic forces is something that we still want to explore even further. Now, do magnets exert a force on all materials? Now, this brings us to something that we may have, interacted with earlier, in our grade, to say that we talk of the uses of materials based on their physical properties, right? Now, there is a wide range of applications or uses of magnets in doors, electric doors, motors, generators, speakers. Now, the type and the strength of the magnet could justify its use in everyday life. Now, the question here is do magnets exert a force on all materials? Now, these materials which experience a force as a result of the magnet, we refer to them as magnetic materials. So now we're talking classification of materials based on physical properties. So we talk of magnetic materials, okay, as well as non-magnetic materials. So if you have a material, it will either fall in one of these two broad categories, right? So magnetic materials are those that will actually experience a force, okay, due to the magnet. And then non-magnetic materials will be the ones that do not experience a magnetic force as a result of the magnet. So the classification is then between these two, which is magnetic as well as non-magnetic. So magnetic materials experience a force, while non-magnetic materials do not experience a force as a result of the magnet, okay? So now you are welcome to try out this. You can use a simple bar magnet. This one is referred to as a bar magnet, okay, because of its shape, right? So it's in the form of a bar, but in both cases, in whether it's a horseshoe or a bar magnet, it's actually gonna be a dipole. Even a horseshoe magnet, which is shaped in this form, okay, that's a horseshoe magnet, it will have obviously the north and the south. Still, it is a dipole. So we want to emphasize that all magnets are dipole, right? But now, these materials that you want to think of is paper. Paper, is it magnetic or non-magnetic? You can try this. If you bring paper closer to a magnet, does the magnet exert a force on the paper? Yes or no? It certainly doesn't. So does wood, okay? Wood does not exert a force, the magnet does not exert a force on the wood as well as glass. But iron, steel, and they are actually magnetic materials. I'm not so sure about copper. You might try with a copper coin. If it does experience a force due to the magnet, then we'll classify it under a magnetic material, right? Okay, now, okay, this is the conclusion. Magnets only exert a force on some materials, e.g. iron, nickel, and cobalt. These three are very, very important. Sometimes we talk about a combination of any of these three elements, which we call alloys, okay? An alloy is actually a mixture, okay? It can be a mixture of these materials, right? Now, iron, nickel, and cobalt, we classify them as the ferromagnetic elements. Why do we call them elements? Because they actually are made up of the atoms of the same kind. So anything that occurs in the periodic table is actually an element. Cobalt is found in the periodic table. Iron, Fe, which stands for ferrous metal, it's a ferromagnetic material, okay? as well as nickel. So these three are essentially referred to as ferromagnetic elements. So any material or object that contains any of these three or a combination of these three, as we have alluded that we speak of mixtures, homogeneous mixtures and heterogeneous mixtures. A combination of cobalt, nickel, and copper still contains iron. So as a result, still becomes a magnetic material. And any material that does not contain any of the three ferromagnetic elements then is definitely a non-magnetic material. So those objects that do not contain the ferromagnetic elements are actually non-magnetic. So these are some of the physical properties. So materials that are affected by magnets are by themselves not magnets, but are called magnetic material. So the issue of language is very important. So we've got two terms here, magnetic materials and a magnet. A magnet is the one that causes, the force of attraction. And then a magnetic material experiences the force of attraction due to the magnet. So that's the two terms are closely related. However, they're not the same thing. They don't mean the same thing, right? Okay, right, moving along. Okay, what happens when a steel pin or a paper clip is in contact with a magnet? Okay, right. Let's say, for argument's sake, we've got a magnet, a simple bar magnet, which is a dipole, north and south. And then this magnet attracts a pin, a metal pin. Now that pin will obviously make contact with the pin. So if say, for argument's sake, we're talking about something of this sort, okay? That's our magnet with the two poles, north, south. And then there is the pin, okay? So this pin actually has been attracted by the magnet, okay? Because the pin in itself is a magnetic material. So this is the magnet, right? And then the pin is a magnetic material, okay? So the pin becomes a magnetic material. But while it is in contact with the magnet, it can attract even more pins, okay? Even more pins. It will attract even more pins to it. Now, this pin acts as what we call a temporary magnet, okay? While it is in contact with the magnet, it becomes a temporary magnet, okay? So not only is it a magnetic material in this case, it's also a magnet in itself. But these magnetic properties that these pins have can only exist while they are in contact with the magnet. The moment the contact is broken, these pins, they cease to be magnets. They only become magnetic materials, okay? So that's a very good observation. Or you can use this in terms of using the coins. You'd realize it actually, you'd come to the same conclusion or observation, okay? So what happens when a steel pin or paper clips is in contact with a magnet? What are we saying? When a magnetic materials are in contact with a magnet, these materials, they actually become magnetized. So the question is, let's put it in a different way. How do we magnetize a magnetic material? And what do we mean by that? If we are magnetizing a magnetic material, we want that magnetic material to behave as a magnet, not only for it to experience a magnetic force, right? Because we're talking about magnetic forces, and forces. So the moment that magnetic material is in contact with a magnet, it becomes a magnet. But that magnetic property would only exist until such time it is in contact with the magnet. While there is no contact, it ceases to be a magnet, which is why we would describe it as a temporary magnet, okay? Right, so that's the magnetization, right? Now, we call them the temporary magnets. So the new term that we have now is temporary magnets. It means these magnetic properties only exist while it is in contact with the magnet. So that's a very crucial observation, all right? Now, how can you change a magnetic material into a permanent magnet, right? First of all, the material must be magnetic, okay? Now, if we want it to be a permanent magnet, we must think about how magnetism arises within a material, all right? Which means for us, the method, if you stroke a magnet with a pin, all right? So the magnet is this magnet that we're referring to is a permanent magnet, and the pin is a magnetic material, right? The pin is a magnetic material. So we've managed to actually discuss this in depth. So the pin will become magnetized. So stroking, essentially, you've got your pin, that's your magnet, you stroke it just like that. But you must stroke it in such a way that it's from the north to south direction, north to south direction. We'll talk about why that is important in our coming sessions on exploring magnetism. But the magnetization process has to be done in such a way that this pin is stroked on the magnet, in the north-south direction. There's a specific reason for that, all right? So the magnetic force will decrease over time. Now, yes, it becomes a permanent magnet, but those magnetic properties will cease to exist as time goes on, all right? So, so if you wrap a copper wire around a nail and then connect the wire to the battery, you will make a temporal magnet, but this is an electromagnet. The big idea with an electromagnet is that there must be some charge or electricity flowing through that wire, okay? And if you use an iron nail, the iron nail, remember iron is actually a ferromagnetic material. So it's easy for it to be magnetized because of its properties, right? So the electromagnet has got many wide uses in real life. We spoke of applications of electromagnets in the scriptures when sorting out metals, and these metals are actually magnetic materials, right? Okay, and in the next session, I'll just challenge you to think about how you can make a compass, which is actually a device. So just on that thought, I just want us to think about that so that when we come back after the break and then we take a deeper discussion on that. So that's as far as permanent as well as temporary magnets. After the short break, we'll look at how exactly we make a compass. Let's take a short breather for now. Welcome back to our third and final segment. We're still discussing, magnetic forces. One of the things that we've already overemphasized is that every magnet behaves as a dipole. Why is it so? Because every magnet has got two opposite poles, which is the north and south, and the interaction of those two poles is what we've also discussed, taken a discussion on in terms of repulsive and attractive forces between, like and opposite poles respectively. So before we went for the short break, we thought about an activity that you may try this at home, okay? Can you make a compass? But let's think about a compass as a simple magnet that is free hanging, which will also at the end, align itself in the north-south direction. We'll talk about why the north-south direction is so important. So what do you need to make a simple compass? You need a magnet, okay? Right, which has got a dipole, okay? So this magnet has got actually a dipole, right? Just go back there. Okay, so it has got a dipole. A magnet has got a dipole. Now, what is a dipole? Dipole is the two poles. So this is a magnet, not a magnetic material, right? Yes, a magnet is a magnetic material, but for a compass, you need a magnet, not a magnetic material. Then we've got a pin for the direction, and then a cork, as well as a small bowl of water. So think about how you can make your own magnet. So this is a challenge that we are encouraged to take, right? Let's move to, so we're still talking about our free, our mind map, talking about the forces, okay? Because what the compass actually does, it shows us the poles that every magnet has got a dipole, which is the north and the south, right? And then let's talk about the origins of magnetism. How does a material become a magnet? Or what's so special? What's unique about a magnet, okay? So magnetism comes from the atom, okay? Let's think about the atom from our chemistry. We know that when we talk about an atom, we're talking about the smallest particle that makes up matter. But within an atom, there are what we call subatomic particles. These subatomic particles, would have looked at them when we discussed the atomic theory, the different models of the atom. But what came out strongly in those discussions was that, every atom has got 3 subatomic particles, which is the proton, the electron, as well as the neutron. The occurrence of the electrons, which is the actual charge that actually explains the origin of magnetism. The movement of the electrons is what is important. But think of magnetism in terms of its origin with respect to the atom itself, right? So every atom has got electrons. These electrons are our negative charges, right? And where do these electrons occur? These negative charges are in the energy levels or the orbitals, and they are always in motion, okay? They are moving. And these moving electrons actually produce a magnetic regions that is called a magnetic domain. So the magnetic domain is a result of moving electrons, okay? So the occurrence of a magnetic domain within an atom or a group of adjacent atoms in an element. And which elements are we talking about here? We're talking about those 3 elements which we refer to as ferromagnetic elements, which is iron, nickel, and cobalt, right? So these 3 have got something that's a little bit different in terms of electron configuration, or how the electron structure of those materials is actually laid out. It's what makes them special in as far as magnetism is concerned, right? So these moving electrons produces what is called a magnetic domain, right? So the magnetic domains are results of the electrons in the atoms, right? Okay. Now, magnetic domains in non-magnetic materials are structured in such a way that they are not aligned. Now, how these electrons move within the adjacent atoms, okay, they are not aligned. Aligned in terms of direction of movement of electrons. This is the arrangement in a typically a non-magnetic material. Remember, we have got 2 classes of materials in as far as physical properties. We've got magnetic, right, and non-magnetic, okay? We briefly spoke about this earlier on. So we've got magnetic and non-magnetic. So these are different types of what? Materials, okay? Right, so if we talk about the domains, this is these arrows, they actually portray or represent the random or haphazard movement of electrons in the atoms of non-magnetic materials. So as a result, if they are not aligned, so we don't have a magnetic domains, which is actually the source or the origin of magnetism, right? Let's move on to something that is magnetic. Okay, so if a material, say iron, right, nickel, as well as cobalt, okay, these are the 3 elements that we identified as magnetic materials or ferromagnetic materials. So that's another term. So nickel will be symbol Ni, cobalt Co. So these 3, we call them ferromagnetic elements. Yes, they are elements because each one of them is made up of atoms of the same kind, okay? So these are ferromagnetic elements, right? So what's so special about them is that these magnetic domains are actually arranged or aligned. So that's the key word, okay? So they are aligned in a certain way, which is not haphazard. So these regions within the adjacent atoms, they give rise to what we refer to as the magnetic domains. So these magnetic domains is actually the core, or the actual origin of magnetism. So for materials that display or exhibit ferromagnetic properties or magnetic properties, it is purely because of the aligned magnetic domains in terms of the movement of electrons. And remember, when electrons or charge moves, what happens? There is that around that material, it becomes magnetic, right? Okay. Now, can you separate the north and the south pole of a magnet? Right. Let's say, for argument's sake, you've got a bar magnet, okay? And what we've also emphasized earlier is that every magnet is a dipole. What do we mean by that? Once again, we are saying every magnet has two opposite poles, the north and south. Now, the big question is, are you able to separate the north and the south pole while we still maintain that every magnet is a dipole? So is it really possible for us to actually separate the two? That's the big question. Can you really do that? Remember, every magnet is a dipole, right? Okay, so it means it has both north and south, okay? The north and south pole, right? So that's what we mean when we say every magnet is actually a dipole. Are we able to separate the two? Okay, it's a thinking exercise, okay? Think about it. So say this is a material of which here we've shown the magnetic domain. Are we able to separate this into two, poles, north standalone, while we have got the south on the other end? That's the big question. So this is, you can try this at home and see if you can actually reach a point where you have the north pole existing in isolation, of the south pole, right? Okay, so think about it. So if we separate it, every small magnet that is broken down becomes two magnets which are dipoles, okay? So actually we cannot actually separate the north pole. So it is not possible, okay? Is it not possible? It is not possible to separate the two poles, okay? Why? We're going back to the point that every magnet is actually a dipole. So it's not possible to separate the two poles of a magnet, okay? So it's not possible to separate the two poles of a magnet. So if we break down a small magnet into two pieces, what happens is these two resulting materials are actually containing north and south pole, maybe different strength because of the size again, because earlier on we've managed also to talk about the factors that actually affect the strength or the size of the force exerted by a magnet on another material, okay? So think about it. If it's like this, it means we still have the two poles, which is the north and south, okay? So it's north to south, okay? North to south. So these two are actually dipoles as a result, okay? So whether you break it how many times, it still remains a dipole. So the two poles of the magnet cannot be separated from each other. All right. Now, what did we say? Okay. We spoke about the three types of non-contact forces. Our main idea, our main focus was on magnetism. We spoke about the non-contact magnetic forces, and we agreed that like poles, okay, are repel, and unlike, which is opposite, poles, okay, attract. But what's so important about that is that all these forces that the magnets, magnetic poles actually exert on each other, they are actually non-contact. For two magnets to exert, or for two poles to actually exert a force on each other, they need not to be in contact with each other. Hence, we are saying they are non-contact. We also spoke in some other session about, we'll talk about electrostatics and gravitational, non-contact forces. There are a number of factors that actually affect the magnitude of that force. But the main thing was that these two forces are either a push or a pull, right? Now, because every magnet is a dipole, we said that these two cannot be separated. It means north and south cannot be separated, right? cannot be separated. So breaking down a magnet into two pieces doesn't mean that we have separated the north from the south. It becomes two smaller magnets, okay, maybe with a different strength, but still the non-contact magnetic forces are still pretty much in existence. All right. Having said that, let's look at the explanation of the non-contact forces, okay? Now, just like the model of the magnetic domains, we've spoken about the magnetic domains of what? Of magnetic materials, okay? Magnets or magnetic materials, all right? All right, and then we use a model of a field. So a field is just actually, a region outside, outside the magnet in which there will be a non-contact force, and the non-contact force is actually between a magnet and another magnet, or between a magnet and a magnetic material, right? So a field is actually three-dimensional. What do we mean when we say the field is three-dimensional? Suppose this is the magnet. So the field does not only exist on opposite ends, but all the way around the magnet. That's what exactly we mean when we say the field is actually three-dimensional, because we live in a three-dimensional space. So if we have got a magnet in space, the magnetic field actually exists all throughout the space around the magnet, okay? So, and we're saying that this, not all types of materials experience a magnetic force. So those that do not experience a magnetic force around a magnet, we call them non-magnetic materials, okay? We call them non-magnetic materials. Okay. So this was in terms of classification, and this is essentially a physical property of a material, right? Okay. Having said that, this takes us to the broader overview. Let's locate our today's session with respect to the broader concept of magnetism. So it's all about the non-contact forces of either attraction or repulsion of the poles. This has to do with the magnetic poles. So these poles, it's your north and south. And we said every magnet is a dipole. Having said that, I think part of our discussion was to emphasize the interaction of poles in terms of attraction and repulsion. We made predictions, we spoke about observation, but essentially we challenged each other to actually try and make our own magnet, our own compass, because the compass is actually a free floating or moving magnet, which is still a dipole. Having said that, and because of time constraints, we've reached the end of today's session. From myself, Themba Ncube, cheers and bye-bye.